general theoretical formula for Manning's N is where R over K is the relative roughness and K is the absolute roughness. R is the hydraulic radius. The absolute roughness is taken as a representative grain size of the particles forming the channel bed. Strickler used the constant 0.0342 in lieu of relative roughness and the median grain size as the absolute roughness to give Williamson plotted the Darcy-Weisbach friction factor as a function of relative roughness to find from which Chesney C can be calculated. The relation between C and N is combining these two equations and using the 84, the grain size for which 84% is finer as absolute roughness, leads to this equation is remarkably similar to the Strickler equation. This table shows Manning's N values calculated with the Strickler formula. The factors affecting Manning's roughness are 1. Surface roughness, 2. Vegetation, 3. Channel irregularities, 4. Channel alignment, 5. Obstructions, 6. Size and shape of channel, 7. Stage and discharge, 8. Season, 9. Suspended bed material. According to the Strickler formula, Manning's N varies directly with surface roughness. The larger the roughness, the larger the Manning's N. Vegetation provides additional roughness, retarding the flow, particularly for overbank flows. Natural channels may require seasonal or annual clearance to maintain the channel and keep the Manning's N from increasing. Channel irregularities such as sandbars, ridges, canyons, depressions, and holes and humps in the channel bed provide additional friction, increasing the Manning's N. In natural channels, meandering may increase Manning's N by about 30%. The presence of obstructions, whether natural or human-induced, increases Manning's N. Log jams and bridge piers increase N. In shallow channels, relative roughness increases, increasing Manning's N. Conversely, deep channels may have lower values of N. In natural channels, friction varies with stage and discharge, affecting the value of Manning's N in a roundabout way. As stage increases while the flow is in bank, N decreases. As stage goes over bank, N increases. For high flood stages, N decreases. In vegetated channels, or in online channels where vegetation has become established, Manning's N increases in the growing season and decreases in the dormant season. The transport of suspended bed material load and bed load consume additional energy, increasing channel roughness in Manning's End. Manning's End can be measured by stream gauging. For a given stream and stage, stream gauging seeks to determine the velocity, hydraulic radius, and energy slope from which Manning's End can be calculated. In practice, stream gauging is limited due to cost and time constraints. Therefore, most applications estimate Manning's End based on experience. Estimates are based on 1. Understanding the factors that affect Manning's End. 2. Becoming acquainted with the appearance of channels whose end values are known. 3. Consulting a table of typical end values shown in books and manuals. 4. Consulting pictorial collections that show channels whose end values are known. The Barnes book, USGS Water Supply Paper 1849, remains the most comprehensive pictorial collection of Manning's End for natural river channels, covering the range 0.024 to 0.075. The Barnes pictorial can be found at manningsend.sdsu.edu. The Arcement and Schneider book, USGS Water Supply Paper 2339, is a pictorial of Manning's End for floodplains for the range 0.1 to 0.2. The floodplain pictorial can be found at manningsend2.sdsu.edu. The lowest possible value of Manning's End is for a laboratory channel made of acrylic glass. For this case, N is equal to 0.008. For concrete line channels, N varies in the range 0.013 to 0.015. For natural stream and river channels, N varies typically in the range 0.025 to 0.075, the smaller values corresponding to the larger rivers. For natural floodplains, N varies typically in the range 0.1 to 0.2. For shallow flows over dense grass or underbrush, N may vary from 0.4 to 0.8. For the Everglades wetland in South Florida, a value of N equal to 1 has been documented. Estimates of Manning's End can be obtained with this formula. Where N sub 0 is the basic value for a straight, uniform, smooth channel. N sub 1 is the value added to account for surface irregularities. N sub 2 is the value added to account for variation in channel cross-section. N sub 3 is the value added to account for obstructions. N sub 4 is the value added to account for vegetation. And M sub 5 is the correction factor for channel meandering. Values of N sub 0 to M sub 5 are shown in these tables.